Okay, next one up, we have our Neurotech panel. And so next one up, we have Mary-Lou Jepsen, David Eeagleman, Randal Koene. Where are you? Randal, are you here? Are you around?
Our slides are
yeah, your slide.
second.
Oh, wow, you already created one. Oh my God, amazing. People are doing it. Todd, hello, hello. And Randal, lovely. Okay, take your seats, guys. And so by this time, you probably already know, this will be hopefully as interactive as possible. So if you want to make a comment, just raise your hand and a mic runner will find you, okay? Just raise your hand, make it chime in there. If you agree, if you don't agree, we want all of that. And then after this panel, we have a break. In that break, feel free, if you have a technology node that belongs to either brain-computer interfaces in Neurotech, this panel, or to long-term space exploration futurism, the other panel, then put them on the whiteboards. We'll be collecting the slides on the whiteboards afterwards, okay? So, all right. Next one up. Wow, we have so much space here, guys. Amazing. Come on closer and so that you can maybe face each other a bit. Okay, let's see. We will have Mary-Lou Jepsen first. So, Mary-Lou, it's your second or third Vision Weekend, I think something like that, if I'm correct. Okay, so you know the drill. And please tell us a little bit about what are you working on in terms of neurotechnologies? Where do you see this field going? And how can people plug in?
Last time I was here, I talked about reading your mind, and really, we're still working on that. We're making devices that we believe, and we can discuss whether that is possible or not here, but there's some good indications, and there should be some good discussion. But we decided it was more urgent to save your mind before we read your mind, although that can be done with a different software layer. So we've really concentrated on diagnostics and therapeutics, moving away from that most expensive room in the hospital that's like a 1950s mainframe era size, the CT or the MRI, they call them initials, they're super expensive, and moving into ambulances and wearable at-home use for various indications. And so the things that enable this, we have something we call phased wave technology, where in the past people have just used the intensity of light. My background is, I have a PhD in physics, I was a computer science professor, electrical engineering, and I've shipped a lot of at-scale, high-volume consumer electronics on the hairy edge of physics. And so I come to starting this company and leaving VR, AR, laptops, projectors and stuff like that with three major observations that enable us to look at the phase instead of the intensity. And so those are really listed up there. The pixel size in cameras is now so small, it's the size of the wavelength of light. And yet everybody says Moore's law is maybe over, but it's a seed change when you can record the waves and the wavelengths of light rather than just the intensity, or both. That coupled with new improvements in diode laser tech, really driven, we're slipstreaming behind lasers developed for LiDAR and some other systems. And then on the ultrasound layer, it's being able to make ultrasonic vibrating things in a standard silicon fab. And I thought those three things were good enough for me to quit my cushy job at Facebook 6 years ago, where I was running advanced consumer electronics, largely for VR and AR and other things, and really look at medical diagnostics and therapeutics. So our first product is actually kind of simple. The number 2 killer in the world is stroke. And it's actually a time to diagnosis problem, and it's a plumbing problem. And so we're actually making holograms ultimately in the ambulance, but right now we're trying it out in the hospitals with stroke victims so that we can make it so that nobody ever has to die or be disabled by a stroke. They'll be able to walk again, talk again, take care of themselves. Right now, 60% of large vessel occlusion patients can't do those. They either die or can't walk or so forth. And it's really just getting the diagnosis right to send them for something called a thrombectomy, because there's this pill you can take. Anyway, there's a lot of detail on it. But the other thing is we found we really seem to be very good in the lab with live slices, for example, on growing neurons for Alzheimer's. and selectively killing glioblastoma cells and not healthy tissue because their cell structure is harder, and so it bursts rather than like a bridge is built for earthquakes to sort of bend. But these cells burst almost like an opera singer singing the right note and bursting the wine glass. But the wine glass with the hard cells for the, like, glioblastoma is a killer cancer in the head. And so we're able, at least in early tests, to do things on that. And also, there's indications this can be helpful in PTSD and anxiety and so forth. So we're working on a suite of tools for that to save lives. But as we add other wavelengths, we get high resolution. For example, oxy-deoxy, we seem to be able to look at other indicators of neurons. So that's really where we've gotten to through pandemic, is save our lives before we read brains.
That's not too bad. Any questions, comments from the audience? All right, next one up we have, oh, there is one? Sorry, yes, just you, go for it.
Hey, Mary Lou, I just wanted to better understand what you meant by read minds. I believe for some time now, you actually can tell one of maybe a couple hundred words that are mapped to a specific mind if they think about it heavily enough, the word or the image. And so that seems like basic. Actually, brain-computer interfacing works through like English words. But what do you mean by read a mind?
It's very crude right now, and there's different implants and also non-invasive technologies that use, you know, for example, Jack Gallant's work in Berkeley, where he used to use rats, then macaques, then grad students. Grad students are his research subjects. They get their PhD if they do it right. But they spend hundreds of hours in MRI machines recording their reactions to videos or sound, or there's a group in Japan doing this where the students fall asleep and they wake up they're awakened every 90 seconds and asked to say what they were dreaming about. And with that, we've gotten are very crude, very grainy images of, word clouds or grainy images and so forth. And so I remember seeing that work about a decade ago saying, wow, we just have to up the resolution and shrink that. And so we're at that point now collectively. To do that measures functional magnetic resonance imaging is what they're using, which is the video form of MRI, the use of oxygen and not oxygen. And the part of your brain using oxygen, that's the part that's working. It's very low resolution. We can increase that resolution. We've created tools to increase that resolution. But that's a slow change. It can take 4 or 5 seconds. And so is that really what you envision when you think of, telepathy? No. There's other people, Elon most famously, but many other people David Eagleman, so you can explain that. Actually, do you want to do a summary? Because I think I think you can do this better.
Which part am I answering?
Oh, yeah, like where we are with telepathy. Or it's crude right now. With the implants, I mean, once you, I just think, Elon is trying to drill a 1-inch hole in your skull and put implants in that can only last a couple months, so you'll need more and more. If you got full-blown, Parkinson's, maybe bring it on, arguably. But I don't think a billion people are going to sign up for that quickly. I think it's going to be non-invasive wearable first. But, eventually, as we work out the bugs.
Yeah, great. I mean, the general story is, right, there's the reading and there's the writing. I'm working on the writing, which I'll talk about in a minute, I think. But as far as the reading goes, there are all these methods for implanting electrodes, either sewing them in or dunking in these hard electrodes. But they're only for a tiny part of the brain, so it doesn't really give you anything about thought or what somebody is, experiencing or whatever. You could just tell a little tiny part of what they're hearing or seeing. So it seems to me we're still a long way off from telepathy. Yeah.
Okay, David, we can't find your slide right now. So
it was slide number 4. Does that help you?
Reload.
Okay, we reload. I love the many of the last action. Okay, we have Christine, Robin.
It was the 4th one for what it was worth. Maybe it got deleted or something.
Okay, well, we'll find it back. In the meantime, we'll have Randal. Randal, please present your slide.
Were you able to find
Yes, I was able to find yours.
All right.
We have you over here. Randal, what are you working on? What do you need?
Yeah, I'll dive into that in just a second. But before I even say that, I just wanted to say that in addition to what I'll just talk about, which is my field, we're actually, so we, as in the CarbonCopies organization, is collaborating with Foresight to set up a Neurotech interest group for the coming year. So hopefully we'll have a lot more going on about neurotechnology in a little bit. So my particular interest is kind of the long term of neurotechnology. It's based on this idea that, you know, the brain is just like every other part of our body, is something that is material and that our mind is emergent from that. So if we are correct in neuroscience that the way that we're studying the brain in a kind of reductionist way, that we're breaking it apart into pieces, trying to understand what the cells do, what the architecture does, and so forth, then you can get a blueprint and you can get an understanding and you can manipulate it and work with it in many ways. Of course, that's what each of these neurotechnologies that we're talking about here has something to do with. So my particular interest is in neuroprosthetics and ultimately in whole brain emulation, which then you can use for whatever you want. But one of the things that people in futurist groups often talk about is this notion of mind uploading, which, yes, I agree with Christine, is still a while away. It's definitely not tomorrow. But then again, you know, time horizons, what are they really? You know, if you look back 100 years, where was neuroscience then? Or what have we done in the last, say, 20, 30 years in that area, accelerating neurotechnology? This field benefits from many of the same accelerators that are accelerating all the other technologies. You know, we're gaining from the fact that we can use machine learning now to analyze data that we're recording and to learn something about the circuits that are underneath and try to do something with them. Given all that, though, there are three main enabling technologies for this. One of them is scanning technology, and that's just a big label. What I work on personally, because my day job is at Voxa, we make these automated electron microscopes, is to be able to scan electron at the electron microscope level, so at, you know, nanometer scale, to scan large volumes of brain tissue. And by large, I mean something like what Voxa enabled recently is Allen Institute's cubic millimeter project, where they scan 1 cubic millimeter of a mouse brain. You get all of that data so you can find out what the connectome is. You can get more than just the connectome. You can see the individual synapses and the vesicles that transport neurotransmitters in there. So you can reconstruct that, but then you just have a three-dimensional image. The other enabling technology is that you need to get a library and understanding of how all of these cells work. You need to collect information about neurophysiology and neurodynamics, and you need to do that for a large number of cells in a lot of different areas of the brain. And then the third part of that is really a compute problem. You're building models and you need to somehow constrain your models. You need to be able to go from having all of that structural data and all of that physiological data and trying to come up with at least small examples, maybe in a fruit fly, maybe in just a C. elegans worm or a retina, some small piece of brain, that you can go from this structure and that function that you've recorded before to something that actually works, that is a model that works, that you could use either as a prosthetic that you can implant somewhere, or that you could use if you want to build, say, you know, an artificial Drosophila brain or something like that. And that's the translation problem. It's the translation from what you measure to the parameters you use in a model, which of course always exists when you're modeling, which is really just hypothesis building in computers. But ultimately, I hope what that leads to is that we get to an outcome where we can not only understand the brain, but we can work with the brain. So you can augment, you can learn, for example, to begin to think at the sorts of time scales that computers think at, see the universe not just at the level of, say, 1/10 of a second, but maybe what's going on at smaller time scales, have real memory, that you actually remember things instead of just reconstructing a vague, possible reality of what's out there, so perceive more of the universe. And also, because you then make having a brain independent of the type of system it's running on, you could have something that is other than a biological body, thereby enabling real space travel, for example, be suited to other environments. So basically, in the end, it's all about humanity being maximally adaptable and sort of having a Cambrian explosion of new intelligences. But that's still a little while away. Let's just say, you know, give it some decades, maybe 100 years. But you know what? If we don't see some major progress in this direction in 100 years, I'm going to be really disappointed in humanity. Because look at what we did in the last 100. It's kind of a big step. So maybe we can do the same sort of thing.
All right, well, we will still have a few, I think, ways to go along the way. And one of the one is definitely that David's working on. So David's working on really cool and really quite accessible stuff already that you can already try out, correct?
Correct. Yeah. So, okay, so my interest is in how the brain ever gets information, and of course it's locked in silence and darkness in the vault of the skull, and all it ever sees are electrochemical signals coming in through these spheres that capture photons, or your ears which capture air compression waves and things like that. And so the thing that's gotten me really interested in the last decade is this question of, can we feed new information streams into the brain? And the enabling technologies are just, the battery density and computational power that we have now to do this. It's actually not a new idea. I found a paper recently from 1928 where people were thinking about this stuff. And actually in 1898, people were also thinking about this stuff. But we're just at a point now where we can push information in the brain easily. And so, first in my laboratory and now in my company, Neosensory, we have built devices with vibratory motors to push information into the brain. And in the case, this is a wristband with vibratory motors around it. It's got pretty sophisticated computational capacity in here. And for example, one of the things that we do is for people who are deaf, we capture sound in the microphone here and translate the sound into patterns of vibration on the wrist. We're essentially taking the inner ear, the cochlea, and transferring it to the skin, and it works. And people who are deaf can come to understand the world that way. And if that sounds weird, just remember that you had to learn how to use your ears when you were born. You didn't know how to use your ears, but your brain figured out, okay, there's these signals coming in, they're correlated with signals from your mother's mouth moving, and when you clap your hands, you hear these signals, and eventually you come to have a direct perceptual experience of it. And that's exactly what happens with this. People who are deaf who wear this for, let's say, 3 to 6 months, then I ask them, okay, what is it like when you hear a dog barking? Do you feel something on your wrist and you think, oh, there's a buzz, so it must be a dog or something? They say, no, I just hear the dog. That's their description of it, which sounds crazy, but that's exactly your experience with your ears. So, but we can do, so that's what's called sensory substitution, where you take one sense that you would normally have and you substitute it by pushing it into the brain, up the arm and up the spinal cord in this case. That's sensory substitution, but I'm interested also in sensory expansion. So, for example, we only see a very narrow strip of the visual spectrum. So I've been wearing a device for a while to be able to see in infrared light. And you walk through a parking lot and you can tell which cars have been parked there for a while and which ones have just arrived because the engine blocks are hot. And you go into, I went to the library and there are 2 chairs and I could tell where somebody had been sitting sometime in the last 20 minutes and where someone hadn't been sitting. And even the books on the library shelf, you can feel which books have been picked up recently and which ones haven't because there's a heat signature on it still. Anyway, it's a huge electromagnetic spectrum, and I think there are probably 12 Nobel Prizes hidden in there for people to discover things. And so we're very interested in, bringing out this technology so everyone can just start exploring other parts of the electromagnetic spectrum. And it's not that, it's not that people don't do this in laboratories, but it's different when you get out in the real world and you're actually experiencing these things. And then finally is sensory expansion, which is building completely new kinds of senses which humans have never had before. So picking up on data directly from the internet or the stock market or Twitter or whatever it is, so that you are experiencing things that that people haven't had before. One of these has to do with electromagnetic fields, and actually I think Todd might touch on that, because Todd actually has done that a while ago. And so these are the things that I'm interested in, and what that leads to is taking the sensory gifts that Mother Nature has given us over a long road of evolution and now being able to build our own. So that's what we're up to.
Wow, fantastic. I think from all the way in the future, all the way back to Earth. And so, Todd, are you doing an intermediate piece? What are you up to? What's your long-term goal, and how can people help?
Yeah, my name is Todd Huffman, and I'm very happy to be here at Foresight Vision. I think the first Foresight event that I attended was in about 2003, and I think that these sort of events are actually very useful for helping people orient into the future. And one of the things that I'm very grateful for was this community inviting me to participate in a workshop on mapping out the technological capabilities between where we are now and whole brain emulation. And so in 2007, Randal, Koene, and Russell Hansen, who are both here, along with about 10 other people, got together for a weekend to map out all the technical components. And one of the things that was very influential for me, I think Robin was the one who did this, was mapping out all of the technical components that need to go into whole brain emulation, and then not just mapping them out, but looking at what were the economic drivers, like what things were Moore's law driven, what things are being driven by the semiconductor industry and different consumer, consumer products. And I chose to focus my career in on the areas that had the least amount of economic drivers. And so if you've talked to me over the last 8 years or so, I was probably talking about automated imaging technologies, and I spent a chunk of time working on that. But very recently, I've become convinced that tissue preparation and cell labeling were areas that had been making advancements. And so Dr. Andrew Payne, who's here somewhere, oh, he's in the back, and Adam Marblestone convinced me that now was the time for cell labeling technologies and tissue preparation technologies, specifically in light microscopy, to really make an impact in neural connectivity reconstruction analysis. And so about 2 months ago, Dr. Payne and I co-founded a nonprofit called E11 Bio. It's a focused research organization focused in on tool development for connectomics. And so we're using, we're integrating expansion microscopy, viral barcoding, and advanced imaging techniques to create a platform for doing neural reconstructions using light microscopy as a complement to electron microscopy. Thanks to electron microscopy, we know that the circuits are there, but the scale of the brain, when you start lining up, what it would take to do electron micrograph level images of whole brains, the scale of the brain is quite daunting. And light microscopy is a lot cheaper, has a lot more potential for scaling, in our opinion, and also very importantly, isn't as toxic to the cells and the proteins, and so it has a much wider range of labeling options. And so what I'm going to spend the next 5 years doing is working with a group of scientists to integrate these and what we hope comes out of this is a platform for doing disease-specific investigations of circuit-based disorders to help with understanding the circuit-based disorders in the brain and to help develop therapeutics. I also think there's a lot of potential for impacting the development of AI and producing better maps of the one intelligent system that we have, or that we know is intelligent, or at least we think we do, the human brain, getting better insight into the architecture of how those neurons connect to each other, and how we can hopefully feed that into sort of neural-inspired architectures and AI. And then I also think that our work is going to be essential for brain-computer interfaces, and as groups develop different ways of interfacing with neurons, these maps will be instrumental, I think, in helping design how these neurons are implanted and how they're configured. And in my sort of key challenge I'd love to see solved, I'd like to see more more interaction between the AI development community and the neuroscience community. And I think what's needed for that are more direct linkages between a sort of synaptic level neural circuit and an AI advance. And I think that as we see these, as the AI community sees these linkages, then that will drive more interest in connectomics outside of just the small subsection of neuroscience that I exist in.
Great. So we already have hopefully a connection between the computing panel later and this one here. So let's see if we can solve each other's challenges. Thank you so much, Todd. And last but not least, we have Jean Hebert. Tell us, is this yours? Yes. Tell us what you're working on.
Okay, great. Yeah, thanks. I guess I could have fit in different categories fairly
You can fit in many different categories, yes.
The neurotech being one, biotech also, or longevity. And what really drives me, though, is longevity. And I'm very optimistic about our ability to defeat aging. I know a lot of people are interested in longevity, and there are a lot of different approaches that are being taken. And I think a lot of those approaches, though, will end up allowing us to live, somewhat marginally longer, healthier lives, but will not defeat aging. And I think the only way that we're really going to defeat aging is with replacements of our cells, tissues, and body parts. The reason for that is just that the damage that occurs with age to our macromolecules, all our classes of macromolecules, is stochastic, non-enzymatic, and highly complex. So to think of ways of manipulating, the body to reverse those without causing more damage is hard to imagine. But replacement, if you replace an old heart with a new heart, it doesn't have any damage anymore, unless you've taken it from an old person. But we're talking about here replacements with lab-grown organs or synthetics. And there's tremendous amount, and the reason I'm optimistic is there's tremendous amount of progress being made in regenerative medicine, tissue engineering, also in synthetic body part replacements. Right? And they're already being used to treat diseases in humans now. So it's a matter of whether we want to start putting them together to reverse all the damage of the body. The reason I'm in the neurotech group, I think, is because, of course, the brain is the most important thing. Organ, one could argue, right? I think we agree on that. And so that's more complicated to replace. It's much more challenging, and I put that as my key challenge. But there's every reason to think that it is replaceable as well, if done progressively. The way that the neocortex works, I'm sure everybody here appreciates, but not everyone at large always appreciates, is the neocortex is sort of the conscious part of the brain, or at least the more conscious part of our brain. It's a very plastic substrate. Things as complicated as language in humans has been shown to move from one part of the neocortex to another over the course of many years when there's damage to the original location. So there's a tremendous amount of plasticity that, at least at a conceptual level, tells us that we can progressively replace the substrate of the brain without losing or disrupting the continuity of function or self-identity. And then again, more recently, with lots of people trying to transplant new cells in the brain, they've shown the tremendous potential of cells to reconnect and form normal circuits in the brain, in the adult brain. So together, both conceptually and in practice, it should be possible to do it. There are many, many challenges. This is a very difficult problem, but it should be doable. So basically, yeah, the key challenge would be the brain, but I would just add to that, too, that Another challenge is more sort of societal, right? I think there's a lot of pushback, and so maybe the existential hope category would also fit. But I think, and I was just talking to Reason about this a second ago, people's perception of surgeries, of replacements, is probably a key challenge that needs to be addressed as well. People are very averse to this idea, even though it could save their lives and allow them to live a lot longer. So I think there's a major challenge there as well, and hopefully we'll get to discuss some of these points.
That being said, congratulations. That being said, congratulations on just getting $1 million in funding, correct?
Yeah.
Well done, well done. So, Jean-Hebert is one of our accelerator projects, and I'm so thrilled that this work that you're doing is finally getting the attention that it deserves. Are there any comments from the panelists on each other? Any heckling questions over here? And we have another one here, like maybe one in the back, this one? Yes. And do you have a comment to each other? Anything you want to disagree with already before we get into the breakouts and you can really have a go at each other or actually enable each other to thrive? Yes?
Do you believe replacing cells in a brain is actually necessary, or could some of the rejuvenation or a lot of it be achieved by just, cleaning up cells or finding a way to correct DNA damage within cells, etc.? So, because I'd be kind of worried about losing state within some of the cells.
Oh, sorry. There you are.
Yeah.
No, I think it'll be necessary to replace not just cells, but the whole tissue. So often ignored, right, is the extracellular matrix, which is hugely important to any tissue, but particularly the brain, because of it stabilizes some synapses and allows others to be more plastic. The extracellular matrix is hugely important. It accumulates lots of damage as well. Even if you could replace the cells, that wouldn't be enough. You'd have to replace extracellular matrix. So you have to replace the tissue progressively. And just trying to rejuvenate cells would not be enough. I mean, if you put young cells in an old brain, they behave like old cells. Right? Those experiments have been done. So they have no mutations. They have a young epigenome. They have good mitochondria. They have everything that young cells have, and yet they still are going to be problematic. You're worried about the reconnection. But again, because of the way the brain works, it's not a static recording. We're very, very functional and plastic. That's why we forget things all the time. That's why we learn new things. Those circuits are changing in our brains right now, and they can change to a new substrate without an interruption in function.
All right. Thank you. Okay, I know you've had lots of questions and lots of hands up. This is just the start where we're getting those ideas out there. Who here is creating a Neurotech node, actually? Who here is working in Neurotech? Okay, we have a few people there. Okay, so you will go around that whiteboard once we're creating it. So what we're doing here on the panels is we're really just like tickling your brain a little to think a little bit about, okay, what are the different things that different people here at Vision Weekend are working on, and then we have them all on whiteboards later today, and then in the breakouts, it's all on you to add your slide and to really figure out how you can help each other within your discipline and across disciplines. Okay, so we've had a lot to digest here already. Thank you so much.